Hello, welcome back to Learn Physics. In today's topic, we are going to continue with our current electricity chapter. That is, in yesterday we learned about this resistivity, that is specific resistance. Okay, that and all we learned. And current density also, I by A, that and how microscopic representation of Ohm's law we learned. And today we are going to continue with our specific resistance, how it will be, or resistivity, how we can explain with respect to its temperature. In metals and in alloys and in semiconductors, how this resistivity will be acting. That's what we are going to discuss now. Okay, so specific resistance or dependence of resistivity on other materials. Okay, so we already learned resistivity will be rho as the representation. Rho we can write it as m divided by n e square 2. So yesterday while I am explaining, I told as temperature increases, what will happen to the relaxation time? Relaxation time decreases. Collision between the molecules will be increasing. Collision is number of collisions increasing means time required between two successive collision will be decreasing. So 2 is decreasing. If 2 decreases, what will happen to rho? Rho will be increasing. So as temperature increases, rho will increase, I told you. Right. So this one, how it will be happening in the case of our metals, alloys and in semiconductors, how it will be happening. Okay. If I am increasing the temperature, rho T equals rho 0 into 1 plus alpha into T minus T0. This is the formula of rho specific resistance at a particular temperature T. Okay, then this one, while rearrange, what is this alpha? Alpha is the new term over here, right? So it is alpha is called a coefficient of specific resistance. Okay, resistivity we can call otherwise as specific resistance, right? So alpha is called a coefficient of specific resistance. So shall we find out one equation for alpha? So from here we can write down as rho equals rho 0 into, so I am this multiplying rho 0 to these two terms, rho 0 plus alpha rho 0 into T minus T0. Okay, this one rho minus rho 0 equals alpha into rho 0 into T minus T0. Therefore, I can write it as alpha equals rho minus rho 0 divided by rho 0 into T minus T0. Clear? So rho minus rho 0, I can write it as change in specific resistance. Okay, that is d rho divided by rho 0 into dt. Okay, so how we can define this specific coefficient of specific resistance? Coefficient of specific resistance is equal to rho 0, that is alpha equals d rho by rho 0 f dt equals 1 Kelvin. That d rho by rho 0 means it is the fractional change in the resistance. What is the fractional change in resistivity? That will be equal to coefficient of specific resistance if we are giving a temperature change of 1 Kelvin. Okay, this is how we will be defining the coefficient of specific resistance. If the coefficient of specific resistance is equal to the fractional change in resistivity, d rho means rho minus rho 0. That is the change which is happening in the case of resistivity because of the increase in temperature. While we are increasing the temperature, resistivity will be changing in such a way rho minus rho 0. Okay, so d rho is the change in temperature divided by change in resistivity divided by original resistivity. So it is the coefficient of specific resistance is equal to the fractional change in resistivity if we are considering a temperature gradient of 1 Kelvin, or increase in temperature is equal to 1 Kelvin. Clear? So here Now, for metals, alloys and this semiconductors, how this resistivity will be affecting. In the case of metals, while I am considering metals, see, rho minus rho 0 will be a positive quantity in the case of metals. Okay, rho minus rho 0, because as temperature increases, what will happen? Rho will increase, I told you, right? So rho minus rho 0 will be a positive quantity. So it is rho minus rho 0 is positive. Therefore, this alpha also will be a positive quantity over there. That means as temperature increases, resistivity of the material, see, first it won't show that much difference, but after that it will be started increasing slightly. It will start increasing slightly. Okay, this is the diagram for it is important. In the case of metals, how as temperature increases, how the resistivity is increasing. As temperature increases, resistivity also will increase. But for small change in temperatures and all, it won't increase that much. But when the temperature increases, resistivity also increases. Resistivity increases, what will happen to resistance? Resistance also increase, because R is equal to rho into L by A. Right. So as resistivity increases, resistance also will be increases. Clear? So here this is the case of metals. Next we are considering for alloys. Alloys, here we are considering two types of alloys. That is one as manganese, other one as nichrome. Okay. In manganese, as temperature increases, the resistivity won't change that much. Okay, resistivity won't be changing that much if temperature is increasing in the case of manganese. That is why we will be using manganese to make the resistors. Okay, to make the resistor, we will be using manganese. Why? Because as temperature increases, resistivity of the manganese won't increase that much, won't change that, it is almost constant. Okay, so now we will draw a diagram. Next we are considering about the alloys. In the case of alloys itself, first I am considering about nichrome. For nichrome, as temperature increases, resistivity will increase. Slightly it will increase. Okay, as temperature increases, resistivity will be increasing. But in the case of manganese, while we are considering manganese, what will happen? As this is rho, as temperature increases, this will almost remains constant. That is why manganese is used to make the resistors. Resistor means to give the particular resistance, we will be using the resistors, right? So if temperature is increasing, if we are giving current for longer time, temperature may increase. If temperature is increasing, how the resistivity increases means resistance there, it will be changing. Then say suppose if I need a 50 ohm resistor and temperature is increasing. While increasing the temperature, 50 ohm is raising to 55 ohm means then what will be? Then everything will be changing, right? All other circuit elements will be changing. So that should not happen in the case of resistors. So we will be using manganese and in making resistors. Why? Because temperature is not having that much dependence with the resistivity in case of manganese. Next is for semiconductors. In the case of semiconductors, what will happen? See, I told you semiconductor means it will be having, it won't be having that many number of free electrons in the valence band. Okay, in the outermost shell, free electrons will be very, very less. Okay, but it's the electrons will be ready to come out from with a very small energy. If it is gaining some energy, the electrons at the outermost shell will be easily coming out from the metal surface. Okay, so if we are giving the temperature, what will happen? These, as temperature increases in the case of semiconductors, these electrons will be coming out to the outermost shell. That is, valence electrons will increases. Okay, number of valence electrons will increase if we are increasing the temperature. While increasing the valence electron, what will happen? Rho equals m by n e square 2. Okay, as n increases, what will happen? Resistivity decreases. Okay, as n increases, resistivity decreases. Okay, so in the case of semiconductors, as temperature increases, resistivity decreases. Clear? So temperature, and this is resistivity. Resistivity will be decreasing as increase in temperature. This is about the resistivity in the case of metals, alloys and semiconductors. Clear? Next, we are going to study about the limitations of Ohm's law. Limitations of Ohm's law. Ohm's law means which this V is proportional to I. The material which obey this Ohm's law is called ohmic conductors, and which are not obeying Ohm's law are called as non-ohmic conductors. Okay. In the case of in Ohm's law, we already told V is proportional to I. Okay, that is V by I equals R. This relation is relevant in the case of ohmic conductors as well as non-ohmic conductors. Okay, but in the case of ohmic conductors, R value will remain same. Ohmic conductors means in the case of ohmic conductors, V by I equals R value will be same always. But in the case of non-ohmic conductors, V by I would be equal to R at a particular point. But in the same metal itself, next point V by I will be, the R value will be different. Okay, V by I will give you resistance value, but that resistance won't be constant in that case. Okay, so next, today we are going to study about the limitations of Ohm's law. So limitations means, see here V and I are proportional, I told you, right? So VI graph, while I am considering the VI graph, here VI is proportional. We will be getting a straight line in the case of ohmic conductors. But if it is not obeying, means it won't be proportional. We will be getting a graph like this. It won't be a linear proportionality, won't be there in the case of non-ohmic conductors. So it's a limitation. And at higher temperature, it won't be obeying the Ohm's law. Okay, as temperature increases, as more current is increasing, means what will happen? Temperature will increase. Then it won't obey Ohm's law properly. That is one limitation. And the second one is, see here, I am considering a VI graph. Okay, in that VI graph, increasing the V and I increasing like this. Okay, it's a linear proportionality is there. But if I am reducing the current, or if I am reducing the current, the voltage will be varying in that case. It won't come through that same path. Okay, so here in the case of a diode and all, while we are considering the diodes and all, we will be knowing, see, we will be studying in the last chapter, semiconductor chapter, you will be studying about this. Okay, as we are reducing the as we are reducing the current, the voltage value will be varying, or we are reducing the voltage, current value will be varying. Okay, clear? So that is another drawback. So next is, in the case of gallium arsenide and all, while we are considering for the same V value, in the case of gallium arsenide and all, for the same value of voltage, we will be getting the many that's a different values of current. Okay, so here it will be like this. That means here for this particular voltage, you see, this may be the current, this may be the current, or this may be the current, this may be the current. So the for the same voltage itself, different set of current values we will be getting. Okay, that is another drawback of this gallium arsenide. Okay, that is another limitation of Ohm's law. Clear? So this is linear proportionality won't be existing for higher values of current, and when we are withdrawing the current, or while we are reducing the current, it won't be coming through the same channel which was going through this. While we are increasing the current, the voltage was increasing, but while we are reducing the current, what will happen? It won't be coming through the same straight line. It won't retrace its path. Okay, it will be adopting a different path. That is a limitation of Ohm's law. And in the case of gallium arsenide and all, while we are considering, for the same voltage we will be getting more than one current value. That is also another drawback. Clear? Next is how we can find out the value of resistance. Okay, finding out the value of resistance. The value of resistance. Resistance value, how we can find out? Using color code. See, if we are considering a resistor, it will be having some ring type colors will be there on the resistor. From that color we can identify which resistance is that one. Okay, what is the value of resistance? See how we can find out. I told each color we have different values. Okay, that is the colors are like this: black, brown, red, orange, yellow, green, blue, violet, grey and white. So these are the colors. These colors, how the values will be going. Okay, here the value of black is 0, brown 1, red is 2, orange 3, yellow is 4, green 5, blue is 6, violet 7, grey is 8, white is 9. Okay, and along with that we will be considering these are the values. Next we have some 3 more colors. One is gold and another is silver, then no color. For this, multipliers will be -1, -2 and it will be representing the tolerance value. Okay, what about the temperature tolerance with that? Plus or minus 5%, plus or minus 5%, plus or minus 20%. So this is how we will be representing the value of carbon. These resistance values are using for carbon resistors. Okay, so the value of carbon resistors, how we can identify from this color code. Okay, see, first strip of this color code will be giving the first significant figure. Second will be representing the second significant figure. Third color will be giving the multiplier. Okay, that is 10 to the power. Okay, fourth one will be representing the tolerance level. Okay, this is how the carbon resistors can be represented. Okay, so suppose if here the color codes are, the colors are like red, black and there's yellow and gold. If the colors are in such a manner, means red red value is 2. Right, so it will be representing the first significant, then black it is 0, that is second significant figure, and yellow is 4, so it is into 10 to the power 4 plus or minus. Next is gold. What is the tolerance value? 5%. Clear? So this is how we will be representing the values of the carbon resistor. From these values, from this multiplier values, we can easily find out. So first you should understand, first color will represent first significant figure, second one second significant figure, third one will be the multiplier 10 to the power, then last one will be plus or minus tolerance level we should give. Clear? So to remember this one, a code value which we are using is, see here, See, this is the code which we are using usually. B.B. Roy of Great Britain had a very good wife. The letter which is given in the capital letters will be representing this one. B, black. Next B, brown. R is for red. O, orange. Y is for yellow. And this G, this O is not there, G. G is for green and B is for blue and V is for violet and next G is for green, gray and this W is for white. Okay, so if this one, if it is in your mind, means you can easily find out this color code. Clear? So this. So that's all for today. Okay, in tomorrow's video I'll be coming with the resistors, series and parallel. So this one is clear for you, I guess, and if you like the channel, please don't forget to subscribe, like and share. Thank you for watching. Bye.